Hi everyone! I've had a few students stop by and each requesting a little bit of help on the liquid chromatography pre-lab. So I thought I'd just kind of start a video to maybe help you guys out. Alright, so make sure you have your lab in front of you and let's check out specifically starting on question number 3. It says, in the liquid chromatography column used in the experiment, the solid has carbon-18 hydrocarbon bonded to it. What that means is that the carbon is bonding to hydrogen. You hear the hydrocarbon. So I know the wording in this lab is not the best, so I definitely want to kind of line that up. So it says, would a C18 hydrocarbon, that means a chain that has 18 carbons on there, all bonded to hydrogen, be polar or nonpolar substance, and explain. All right, to help you out, you may want to check this out. This is a list of electronegativity values. You can find these all over the internet, so this is nothing special. You guys can look these up. Remember, the word electronegativity just basically is talking about the pull that an atom has for another atom's electrons. So when you have an atom sitting here and the positive nucleus in the center, and then another atom over here, positive nucleus in the center, as you bring these guys closer together, each of the nuclei, the positive ends right here, they have a certain amount of pull for the other, or attraction, if you will, to the other atom's electrons. So as you bring these atoms closer and closer, this guy's nucleus is going to be able to see the electrons on the other atom and be attracted to it. There is a general guideline to kind of help you figure out whether or not two atoms will create a polar bond or not. So the general rule is when you're looking at these electronegativity values, carbon is 2.5 and hydrogen is 2.1. When you're looking at that, what you do is you get the difference between the two values, between the two atoms. So the difference here, if you just subtract, the difference here is 0.4. That is the difference in their electronegativity value. Here's a general rule. Bonds are said to be mostly nonpolar in characteristic when the electronegativity value is between 0 and 0.5. They're said to be polar when they have a difference between 0.5 and 1.9. And then they're said to actually be ionic. You see, once you start pulling really hard on that electron, it'll eventually rip off. It's said to be ionic when it has a value of 2.0 or more. Now, this is just a general guideline. In fact, many scientists kind of disagree upon this general rule here. All right, so let's just look at the difference here. You have a difference of 0.4 in electronegativity. According to this general guideline, it's not very polar. This is more of a nonpolar kind of characteristic. So we're going to say that the bond between carbon and hydrogen is nonpolar. So that should give you a good answer on question number 3. All right, everyone, let's move on to question 4. Question 4 just makes sure that you understand that the Kool-Aid is definitely a mixture of different types of compounds with different types of polarity. So they have all of these things and they want you to group them as being very polar, kind of in between kind of polarity, or nonpolar. So you're not expected to look up a bunch of the electronegativity values on any of these. I wouldn't expect anybody to actually do that. And if you look into the background information, they give you very limited information about the components of the Kool-Aid mixture. So I was a little surprised at this particular lab at how little information they gave you to begin the lab. This is not typical. Usually these labs that I give you have an extensive background area, and that's why I felt necessary to do this particular video to help you guys out. All right, so I'm going to help you guys out quite a bit here. So we have things listed here that need to be categorized, and so I'm going to help you out. The most polar compounds, POL, the most polar compounds that we have listed here are going to be your citric acid. So I want you to think about the structure of an acid. Usually you have like a hydrogen in the front, and then you have this acid sitting on the back. Well, acids in and of themselves, what they like to do is they like to take their hydrogen right here, and in solution, they like to pop it off. And that, in essence, is what makes an acid, are these hydrogen ions that float around in water. So our citric acid, we are going to list as being, highly polar. So citric acid should be listed as highly polar. All right, the next thing that you need to look at is, let's take a look at salt. So NaCl. Who knew, right? We actually have salt in here. Now, the word salt doesn't necessarily mean NaCl. In chemistry, the word salt actually means anything that is ionic. I don't know if you knew that. So it may not necessarily be NaCl. It could be anything really that is ionic. Ionic compounds, if you remember, their electronegativity values are, the difference between their values have to be a difference of 2 or more, right? 2.0 or greater. So anything that is ionic, that is soluble, able to dissolve in water, we will be listing also as being highly polarized. All right, so citric acid is polar. Any salts that dissolve in water are polar. Let's look at this next one, maltodextrin. I would never expect you guys to actually look this stuff up, but why not? So maltodextrin, as you can see, is a polysaccharide, and it's used as a food additive, and sure enough, Kool-Aid's got it in there. So this is the basic structure of maltodextrin. It looks like we've got like these hydrocarbon chains, but I don't know if you guys remember me telling you this in class, but anytime, and I hope I said this to you guys, anytime you see these OH bonds, do you guys see that right there? Anytime you see OH bonds, remember what I said, those stick out kind of like a sore thumb. It's like a sonar, like radar to all the other chemicals that are in its area that, hey, I'm ready and able to bond. OH is a fairly polar bond. So we're going to be listing maltodextrin underneath the polar category. And I bet you want to know a little bit more, so why not? Maltodextrin is sometimes used in food to kind of increase the texture of the food. It's used in beer, it's used in, potato chips and jerky. Anyway, I thought you might find this fascinating. It is also used in light, quote, light peanut butter, with the reduced fat. But to keep the texture, what they had to do was to add a little bit of maltodextrin into it to keep kind of that heavy thickness into the flavor. So I find it fascinating that they decided to put maltodextrin into, come on, Kool-Aid? Like, we need texture in our Kool-Aid? Doesn't really make sense to me, but hey, who am I to disagree with a marketing frontier that has made so much money, right? Kool-Aid? Interesting. All right, the last compound that we are going to categorize as being polar is the last one. It's called ascorbic acid. Okay, here you go again with this acid. So just remember, like I said, acids typically have that hydrogen in the front. As long as the acid is able to dissolve in water, it's going to make those hydrogen ions. Guys, acids are typically listed as polar just as long as they're able to dissolve, because we do have these things called fatty acids, and fatty acids are not very soluble in water. And the reason why they're not very soluble in water, remember how I told you that water is polar? Okay, and if a compound, polar, and if a compound is not able to dissolve in water, guess what that means? It means that it's probably non-polar if it cannot dissolve in water, polar. So what that means to me is we have this other compound listed. It's called calcium phosphate. Calcium phosphate, yes, it is ionic. You hear the calcium in there, but you probably never thought to think about this. Calcium phosphate is not able to dissolve in water very well. It's not very soluble. So because it's not very soluble, I'm going to classify calcium phosphate as being a nonpolar substance. The next one that we want to talk about are the dyes. And the pre-lab did talk pretty much mostly about those dyes. And the reason why we can separate out the dyes so well is because they are moderately polar. And I think you're going to be able to tell through the lab who has a higher polarity and who has a slightly less polarity. It'll be actually pretty cool. So we're going to classify those dyes as being intermediate in polarity. All right, the other thing that we are going to look at are the flavoring oils. All right, just the word oil in and of itself should help you to go, aha, oils don't dissolve in water. So we're going to need to make sure that you remember that the oils are mostly non-polar because they're probably going to float in water. All right, guys, I hope that helped. Let's move on to question 5. Question 5 just wants you to suggest maybe a different mixture that we could use liquid chromatography to separate. Guys, any two substances that are in a mixture that have varying polarity, anything that has varying polarity like that, you can be using liquid chromatography. So here's something kind of interesting too. The human eye is used as a detector in this lab. We will be looking at color. You know, as the dyes come through, we can actually be able to tell which dye came out first. So the columns might be used to separate like inks in a felt tip marker or any kind of mixture of dyes because you can see the color. All right, so that was just a suggestion for that answer. All right, on to the hard one. Question number 6. So they gave you some data for the experiment, and 1 milliliter of Kool-Aid solution was loaded into the set pack, and it says the red and blue dyes were eluted, that means pulled through, from the column with a consistent flow of 18% isopropyl alcohol. The eluted solution was collected in a 10 milliliter graduated cylinder. The volumes of eluent were recorded at the beginning and end of each color band. All right, let's talk a little bit about the vocabulary here. Okay, so the stuff that we use to pull the liquids through the chromatography column, the alcohol, that is called the solvent. All right, your solvent is an alcohol, and I think I made this point. The alcohol is relatively polar. So remember, like dissolves like. Anything that is highly polar is going to be attracted to your solvent and want to move with the solvent. Anything that is listed as nonpolar, they're going to be more attracted to the actual stuff inside of the set pack, the C pack. You know, that nonpolar, that white material that's inside of that little chromatography piece. So you see what I've got here? We have something that is moving through the column that is relatively polar. It's going to attract all the polar molecules in the Kool-Aid and pull that through. Anything that slows down, that doesn't want to come through, that must mean that it's relatively nonpolar. The more polar compounds, the more polar substances are going to come through the column first. So anything highly polar will come out first. Anything moderately polar will be next in line. And anything non-polar, they're going to spend the most time in the column, and they will be the hardest ones to push out. So this word, eluent, I'm not even sure I'm pronouncing it right. An eluent, this is the volume of the material that pulled through. So you know how we're going to pull out different colors of each dye? This would be where you go, aha, I see this particular substance in here. This is the stuff that actually comes out the end. This is like a collection of separated materials, if you will. So this is the volume of separated material. Okay. So as things are separated through the column, you're going to collect that. Those small collections that you separate out, those are called eluents. All right. So when you look at the red dye data table that they gave you, make sure you have your lab in front of you. You did the red dye in 3 different runs. Okay, so you did the red dye 3 different times. So I'm going to do for red number 1, for trial number 1, we're going to look at the bandwidth. Now, all of this math that you're doing here on this pre-lab is just basically math that symbolizes how effectively you separated the dyes. So keep that in your back of the mind when you're like, what are we doing? We are mathematically determining the effectiveness of the separation. So in the first run, it looks like red started to come out of the solution starting at 1.0 milliliters. It looks like it stopped coming through at 1.8 milliliters. So if we're trying to find the extent of the bandwidth of when red came out, we are going to take the 1.8 milliliters, which is where it stopped, and we are going to subtract that initial volume where we started to see red. That would be 1.0 milliliters. So the bandwidth on trial number 1 is 0.8 milliliters. That's what bandwidth means. Let's look at blue. Blue on trial number 1. It looks like blue came out second. You can tell, right? The bandwidth on the first trial started at 2 milliliters and ended at 3.8 milliliters. So I'm going to take the 3.8 milliliters and subtract that from the 2.0 milliliters. And it looks like that would be a 1.8 milliliter bandwidth. So it looks like blue has a larger bandwidth than red. You see how that's working? You'll want to continue calculating all the bandwidths all the way through for each of the trials for red and blue. So that should help you with number 6, part A. Let's start looking at number 6, part B. In part B, they want you to find the very center of the band where most of the dye was pouring through. Okay, so you started with the bandwidth in part A. To make the math a little bit easier, at this point, what I would actually encourage you to do is go back to part A. You had to do 3 bandwidths, 3 for red, 3 for blue, and to make your math just a little bit easier from this point on, why don't you calculate the average wavelength from part A? So I'm going to show you the red bandwidth, okay? You should have gotten 0.8, right? 0.8 for one of the bandwidths. And here's some of the other ones. You should have also gotten 0.7 and 0.8. So add those all up and just divide by 3 to get an average bandwidth. The average bandwidth for red was 0.8 milliliters. Let's use that now for part B. It wants you to calculate the center of that bandwidth. The thing that you have to remember is that when you calculate the center of the bandwidth, we want you to remember that it took 1.0 milliliters to even start seeing the red come out. So in order to calculate the center of the bandwidth, you have to include the starting volume, which if you look back at trials 1, 2, and 3, it looks like they all pretty much started at about 1 milliliter. So you need to take that starting volume where you first saw the dye come out and add half of your bandwidth, half of 0.8, okay? And I think you can do this in your head. The center of the bandwidth would be 1.4 milliliters. You also need to do this for the blue dye. And if you did your math right, if you look back at the trials, it looks like the blue on average started at about 2.2 milliliters. You need to add half of the average bandwidth that you calculated from part A. And I'll give you a big fat hint, it should be 1.9. Okay? So the center of this guy's bandwidth was 3.2 milliliters. Basically, the information that you just calculated is giving you kind of the effectiveness of the separation. So we started to see the red pull out at 1 milliliter, and the center of the bandwidth was about 1.4. This was the center of the bandwidth. So if I can do a good job here at drawing, we could say that maybe that first hump looked like this, and this was the red. And you can look in your lab book, right? The center of the bandwidth was about 1.4 milliliters for the red. And the blue, it looks like it started at about 2.2, so maybe about right here. And the center of the blue was at about 3.2, right? Center was right here. So this is a much broader bandwidth. And so this will be like much broader right here. And there's your blue. So can we say with a certain amount of degree of certainty that we were effectively separating these two dyes? Do you guys see how there's a blank spot right here? That's good. That means that we had an effective separation. All right, so let's go on to part C. So in part C, they want you to calculate something called the capacity factor. The capacity factor is just basically a number that represents how attracted the dye is for that set pack material. You know, this is kind of like a way to measure the overall polarity of the dye. The higher the value, the more non-polar it is because it can be stuck inside of the set pack. The lower the value is, that means it's more polar and it wants to push through first. So I think you can already tell from the data that red came out first, right? So we're expecting our red dye to have a low capacity value, and we're expecting the blue dye to have a very high capacity value. They gave you this really groovy formula, all right? Basically what we did is we're gonna take the center of the band where most of the dye was coming out, right, from part B. We're gonna take those values and we are gonna subtract the volume of the actual set pack from it and then divide that again by the volume of the set pack. All right, I know it sounds a bit confusing, but let me just help you out with the red dye part. Okay, so the red dye, we had the center of the band happening at 1.4 milliliters. This is where most of the dye was coming out. We are going to subtract the volume of the set pack, which they gave to you. They said that the volume is 0.49 milliliters, but if you look at the sig fig here, you see how this guy only has 1 decimal. The value is 0.49. If you want to just kind of round that to just 1 decimal, you can. So I'm going to go like this, milliliters. And you divide that by the 0.5 milliliters here. And so the red dye has a retention value of 1.8 milliliters. Now if you do that for the blue, all right, I'll give you some help here. Let's see, check your work. The center of the band was at 3.2 milliliters. Again, subtract the volume of the set pack and divide again by the volume of the set pack. The blue dye's retention value is 5.4 milliliters. So it seems like the blue dye is attracted to the material inside of the set pack. That means that the blue dye must be a little bit more non-polar than the red dye, because red dye came out first and the blue dye came out second. In part D, they're looking for something called a selectivity separation factor. They symbolize it as alpha. Hey guys, seriously, all this value is an indication of whether or not you had a good separation between the two dyes. We want the value to be between 2 and 10 to indicate a good separation. So if you have a value that is less than 2, you had poor separation, very poor. And the way that they do this is they want you to put those, do you guys remember those retention values? We want to put those retention values into the form of a fraction. And you always put the larger value on top. We don't have any separation factors that are less than the value of 1, okay? So we're going to put that larger factor, look back at part C. The blue dye had a factor of 5.4, and the red had a factor of 1.8. All right, and this gives you a separation factor, or selectivity separation factor of 3.0. That means you had a pretty good effective separation. In part E, they want you to calculate something called the resolution. This is a measure of how well the two dyes are separated by the column. You know, how effective was the column at separating out the dyes. And they give you a pretty groovy little formula. Don't want you to worry too much about it. Let's check it out, okay? What you have to do is you have to take the center of your band, which we calculated in part B, take the center of the band and subtract the two values. Then you have to divide by the overall wavelength of each of the dyes and take those, add them up, and like halve them. You got to put them in the middle and halve them. All right, so let me just kind of show you how to do this. So again, this is resolution. They symbolize it as R. On the numerator, let's take the center of the bands that you calculated in part B. All right, the blue had a value of 3.2. The red had a value of 1.4. Okay, those are milliliters. And then on the bottom, we're going to take half, see how I'm doing the 0.5, and we are going to add the wavelength of the two. This goes way back to part A, okay? We're going to take half of the 1.9, that was the blue wavelength. Remember, it was a really fat wavelength. And let's add that to the wavelength of the red, just like that. You should get a value of 1.3. So what does a value of 1.3 actually mean to you? The numerator is basically the volume between the band centers, right? And the denominator represents the average bandwidth, okay? The greater the selectivity, you know, the value here, the larger the numerator is going to get. And therefore, the greater the resolution. You're looking for this value to be larger than 1. The more larger it is, the more effective you were at separating. All right, everyone. I really hope this has helped you out quite a bit. So please take this lab as just understanding that we're trying to effectively separate solutions, and all of this data stuff that you just did is a measurement of the effectiveness of the separation. I hope this has helped. Bye, guys.